seeing in the multi-sim simulation is a 8-bit digital to analog converter. The bottom left, we have a analog to digital converter. This will take a analog 5-volt peak-to-peak sine wave and output it as a digital format. And it does this by having 8 pins. And so it has a resolution of 256 values. So that will output it in binary. And then it'll come up to the R2R ladder and convert it to an analog voltage level. From there, we'll go into the op amp and we can introduce some offset by injecting some voltage into the non-inverting terminal. And then we can have also a gain. Here we have a gain of 3 for the op amp. This is a 741 op amp, the one we'll be using. And we have a plus minus 9 volt rail voltage. So we can get values into the negatives. And if we run the transient analysis, you should see, there you go. So the output voltage traces the input voltage. It is a bit slow, nearly finishing up. And as you can see now, we can zoom in and see the individual steps. And you can see this is a very high resolution digital to analog converter. But that green is the output. So there you go. Now we're over into Tinkercad where I have a mock-up of my physical circuit. And most importantly, the code that I'm using is right here. So all I've done is initialized all the output pins so that they're 0 to 5 volt. And I have my array that maps a sine wave. And where I got that from is just from a sine lookup table. It could have been any inputs. Maximum amplitude is 0 to 255 because there are 8 pins. And then it spits out a array which perfectly maps a sine wave. If you wanted to adjust the frequency of this wave, you can obviously adjust the number of points, which gives you a lower, which would give you a more choppier sine wave. But one of the ways I found was just to adjust the delay in the seconds. And then how it creates these values into binary is it's a combination of a for loop and then an AND comparator to achieve the least significant bit. If I run this code, you can see that we should get a beautiful sine wave. That should have a frequency of 11 Hertz. But as you can see, it's fluctuating from, you can't see because of the refresh rate, but it's going from +5 to -5 volt. So before I connect my output pins 2 through 9 to the DAC, I just wanted to show you a quick visual representation of all the pins working properly. And I've done this by hooking them up to LEDs. So currently this is just cycling through an array of 0 to 255, and it's showing it in binary from the least significant bit to the most significant bit. So here we have the physical circuit, and we have the output connected to the DAC, and then we have the op amp being powered by -9 volt, and then we have +9 volts, so we can output ranges in the negative, and then we have a 5 volt offset voltage, and from this we are generating a 11 Hertz wave with a 5 volt peak to peak, which can see delta 10 volt, and if we unpause this, you can see that it runs smoothly off this physical circuit. Now we're back into the multi-sim simulation and going to make the PCB, and I just wanted to just iterate that the ACD, the analog to digital converter, is not part of the DAC. Okay, so when we go over to make our PCB, notice that we have all the input pins 1 through 9. Now if we put this on the PCB, we end up with something like this. This is the op amp, the positive and negative rail. We have our -5 volt to offset the signal, our V out, our R2R ladder, a couple more resistors, and our input pins rated through to 9, as you can see. And if we go to the 3D view, you can see that's exactly what we've done. So this is the final product, and all that needs to happen now is it just needs to be printed, and then it's done.